Okay, why don't we go ahead and get started? Hello and welcome to our second live webinar. The subject of today's webinar is an introduction to using Python scripts to add capabilities to both FreakC and to FAST. I'm going to make a few assumptions for today. First, I'll assume that you all now have at least some familiarity with both FreakC and FAST. And in particular, that both of these simulators operate using keyword block-based text input files. The second assumption is that you have some basic understanding of Python scripting. I realize this assumption can be an issue. In the past, some students have known Python pretty well, but many have not. Others have had some experience with scripting with other languages, such as MATLAB. With this in mind, I'll try to keep this at a fairly high level. For those who do not work with Python directly, I hope that you will at least see the opportunities that exist to extend FreakC and FAST models beyond the simple input file setup that can be done by hand. As with the last webinar, I have a few housekeeping items to go over first. One is that this webinar will be recorded for later playback. If you wish to listen to something again, or if you need to leave early today for some reason, please mute your microphones to help reduce background noise. There will be an opportunity to ask questions at the end of today's webinar using the chat feature here in the BlueJeans app. And then finally, the slides from today's webinar, as well as the supporting FreakC and FAST input files and the associated Python scripts we'll be discussing will all be distributed later via the class announcement forum. So first off, how can we use it to enhance model productivity? Well, there's a number of items that we should think about in terms of where scripting can help us. One, the most obvious one, just ease of use. Again, both FreakC and FAST operate using text-based input files. So we can automate this process using a script to assist in putting together input files for very complex model setups where there is a lot of tedious work involved and the opportunity for typographical errors to pop up. So scripting can help with that. Scripting can also help with batch processing. This would involve, for example, running a large number of model realizations to evaluate parameter sensitivity. This would be, so-called Monte Carlo simulation, and we have an example of that we'll go through today. And then finally, scripting can enhance model capabilities. This would involve performing some external calculations and incorporating the results of those calculations into the model setup. So why Python? Why use Python for a scripting language? It offers a number of advantages. It's relatively easy to learn compared to some other languages. It supports an object-oriented programming mindset if you prefer to work with that. And most importantly, it offers an array of scientific computing libraries that can be used for all sorts of calculations to support your FreakC or FAST model. So examples of these libraries would include NumPy. This is to speed up calculations. The Pandas library, which allows you to handle model input and output as data frames. The SciPy library is wonderful. It has tools for interpolation, numerical integration, solution of differential equations, and so forth, and we'll see some examples of that today. And finally, there is a plotting library, the Matplot library, to help review results that you may generate on the fly. Okay, so as far as FreakC goes, there are different approaches and different tools available for developing scripts, or more sophisticated programs for that matter. I would divide these up loosely into sort of hard coupling and soft coupling approaches. Hard coupling entails embedding software tools into your application that allow you to directly access FreakC capabilities or keyword blocks. There's a number of ways of doing this. These include the FreakC RM library. This is a set of C++ libraries that allows freq-c functions to be called directly from Python, or for that matter, Visual Basic, Excel, Fortran, other environments. This requires a C++ compiler and some knowledge as to how to use it. ifreqc-com, which is the same idea as freq-c-rm, but this comes with pre-compiled libraries that you won't have to directly sort of mess around with a C++ compiler. However, this particular package is for the Windows environment only, which can be a limitation for some folks. And then finally, there is freqc-py, or freqpy, excuse me. This is a Python library that you can add to your Python installation, which also allows you to access freq-c functions. I have not worked with it, and I'm not sure to what extent it is being maintained, but I thought it warranted mention here. Each of these three hard coding examples I just went through, you can see the links here on the slide. These can all be downloaded from the basically the freq-c website that's put together by the USGS. So the advantage of these hard coupling approaches is computational efficiency compared with the soft coupling approach, which I'll get to next. The disadvantage is computational complexity. Each of these tools that I've just mentioned require some degree of computational expertise beyond the geochemical modeling skill set that one would need just to run freq-c. There are individuals out there who can meet this requirement, but by no means does this apply to everybody. In addition, some of these packages can run into dependency problems when other packages that are required aren't present on your computer. In contrast with the hard coupling approach, the soft coupling approach is much more straightforward to implement. It really just involves reading and writing of text-based input and output files. In keeping with this simple philosophy, this approach is probably a better way to go in an introductory class such as this one, so this is what we'll be using. The disadvantage in this case is that inefficiencies can pop up, such as having to repeatedly reinitialize portions of freq-c or fast simulations. So the particular applications should be chosen carefully. So the easiest way to introduce scripting with freq-c and fast is to walk through some examples. So we have one for each model that is included in today's webinar. The first example concerns the earlier trace metal adsorption-desorption example with freq-c that's discussed in Module 5 in the class materials. That particular aquifer water chemistry or water quality model actually makes a pretty large number of assumptions about things like adsorption site density, that the values of the complexation constants supplied with freq-c are representative. In reality, these are based on very specific controlled laboratory conditions, so may or may not be that representative at a given site. And we're also assuming that the background trace element concentrations are representative. And recall that these are used to populate the initial adsorption sites. In reality, of course, all of these numbers are uncertain. A Monte Carlo approach, which allows multiple realizations to be run using slightly different assumptions for the values for each of the model inputs and parameters, can be instructive for understanding this uncertainty. The second example concerns a fast simulation. As you may recall, fast really only models saturated groundwater flow. Any dry cells that might exist in a fast model are treated in a similar manner to dry cells in ModFlow. For those of you who are familiar with ModFlow, water is passed through dry cells to underlying wet cells, but that's really it. There is no built-in modeling capability for unsaturated flow via the Richards equation. This is where scripting comes in. By performing unsaturated flow modeling externally to FAST and passing some of the output from that model to FAST transport input file, FAST can be sort of fooled into indirectly solving for unsaturated flow. The specific example involves nitrification and denitrification, so more on that in a bit. So in summary, the model desorption response, and we're talking here about example number one, the model desorption response of trace elements to acidification roughly matches observation, at least when the data are sort of lumped together and averaged. And again, we're talking about the application that was discussed in Module 5 in the class materials. However, as I just noted, specific predictions reflect multiple layers of parameter uncertainty. So one approach to help understand this parameter uncertainty is to run multiple trials, with each trial consisting of slight variations on equilibrium constants, adsorbent masses in the aquifer mineralogy, complexation site density, and initial concentrations of certain elements. On a conceptual level, at least, this seems pretty simple. However, this would be extremely tedious to do by hand. It turns out that setting up and running Monte Carlo analyses with freq-C is probably one of the simplest things that you can do with Python. So we'll start with this example first. The first step is to develop probability distributions for the model parameters that are to be varied. These would include, for example, ranges of log equilibrium constants for the various surface complexation reactions, or ranges of background groundwater concentrations of trace elements. There are, of course, statistical functions within the Python computing libraries, such as SciPy, to do this for you if you have a set of data points to fit. For this exercise, we're simply going to posit some distributions as a demonstration. These would include normal distributions for the surface complexation constants on hydrospheric oxide, gibbsite, and manganese oxide as adsorbents. And I should mention that, as you know, freq-C uses log K values for complexation or equilibrium constants and not the actual values. So these normal distributions are really log normal distributions, but that's just a detail. And we're also going to assume uniform distributions for initial concentrations of various trace elements, masses of equilibrium phases that act as adsorbents, surface complexation site densities, and the amount of sulfuric acid reactant that is released into the aquifer mineral assemblage solution blend. And again, if you need a refresher for this, you can go back and look at the material from Module 5 after the webinar is complete today. So in terms of the mechanics of the script, we first need to consider the problem of writing an input file for freq-C and automating that. The original input file taken from Module 5 is shown in the screenshot on the left. A surface species keyword block is used here to define surface complexation constants for the hydrospheric oxide phase. Python can read a file line by line and parse that line as delineated by spaces, tabs, commas, or other characters. So one approach is to search for certain keywords, such as surface species, activate a flag in the script, and then look for numbers that follow specific strings or subsequent following lines, such as log K. Python can then replace the number with another that is selected from an associated probability distribution. A replacement input file is then constructed line by line using this procedure. An example is shown on the screenshot on the right. So let's look in a little more detail as to how to accomplish this. So here is a portion of a Python script written specifically to read and modify the input file for the Module 5 problem, as I'll refer to it here from now on. Starting at the top, lists of keyword flags are defined, along with standard deviations used to vary the surface complexation constants. There is also a list of components defined for which the initial concentrations will be treated as random variables. The for loop involves a pretty simple sequence. And this is generate a new input file, run freq-C using the subprocess function, read the output file, and tabulate the results in a data frame for later plotting and exporting to summary text files. I should stress that the batch version of freq-C, as opposed to freq-CI and its integrated user interface, must be installed for this